all right, how are we going to do this bit? Well, basically, you need to be aware that this can also be written as well. I'm going to expand it out. And then you can actually distribute the sum to each individual term. This is going to be 4 times the sum of the squares minus 4 times the sum of r plus the sum of 1. Now, of course, since I'm summing each of those things to n and I have the various formulas, I can, plug those in. What's this? You might wonder. I'm adding up 1 n times. What could that be? And we see it's going to be n, if you think about it for a second. It's just going to be 1 plus 1 plus 1, da 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 da, plus 1, and 1s. It's going to give me n. So, yeah. Now, over here, I'm just going to plug in these expressions. So, the sum of the squares is 4, 6, n plus 1, 2n plus 1. Okay. Minus 4 times a half, n plus 1. And hopefully that will reduce down to what we're given. But look at it. We wanna force it to be this. Just force it, right? So a third n. First of all, what am I gonna do? Right, this is a 2. Right, this is a 2 over 3. I could factor out an n out of the whole thing. Okay, so if I factor out an n out of the whole thing, and I factor out a 3, what's left? Gonna be 2n plus 1, 2n plus 1, minus 6n plus 1, plus 3. Yeah, I think that's pretty sound. So, what's this gonna be? Well, we see this is gonna be 2n squared plus 3n plus 1. I'm going to expand that out, right? And what I'm going to get is, it's going to be 4n squared plus 6n plus 2 minus 6n minus 6 plus 3. It's n over 3 times all of that gunk. All right. Now you see that the 6n's will cancel and go away. Plus 2 plus 3 and minus 6. So all of that comes together to give me minus 1. So that's n over 3, 4n squared minus 1. This is the difference of two squares. So writing it as such will allow us to get exactly what we wanted. Interesting. All right. So what we want to do now is simply use that formula. When we're doing this here, we look at the limits. Okay, we've already calculated this up to n. Now we look at the limits. We want it to go from 3n to n plus 1. So if you think about it, if I plug it in for 3n, if I plug in the number 3n, then I plug in the number n, and I take it away, what's left? Well, it's simply n plus 1, all the way up to 3n. Exactly what we want, right? So if I call this expression the sum of n, I'm just going to calculate, I guess, the sum of 3n minus the sum of n. So you're just going to substitute both of those things in. And what are we going to get here? Well, the first one's going to give me n upon, well, 3 squared is now so 36. N squared minus 1 minus n over 3, of course, just the thing itself. Let's try and simplify that a bit. So again, let's take an n over 3 outside. I'll change my pen a bit just to spice things up. Okay, so n over 3 comes outside. Now, if I want to put an over 3 there, I need to times this guy in here by 3. So it's 108 n squared minus 3. Then I'm going to have a minus 4n squared, and that's going to be a plus 1. So what does that equate to? Well, it's going to be 104n squared minus 2. I can factor 2 out of that, giving me a final answer of 52n squared minus 1. And we're done finding A and B to be integers, 52 and -1 respectively. All right, so we see here, it's a parabola question. Okay, so we want to find the equation of the directrix of C. So in our general parabola, it looks a bit like this. The equation of the directrix is minus A. Okay, x equals minus A. With focus A, an equation y squared equals 4ax. That's me generalizing a parabola and getting things in terms of A. A lot of people wondered when they were given this definition why there was a 4 next to the A. Well, because it led to these. You know, if you have y squared equals ax, it's going to lead to the focus being at a over 4 and the directrix being at minus x equals minus a over 4. They were like, oh, but a is a constant. Well, it's defined as such, though, that the other expressions are easier to handle. You know, it's more convenient. So we don't do that. Now what you usually do is, when given any parabola, you calculate a. So a is kind of, A is your price tag of your parabola. You know, it kind of tells you a lot of things about it. 12, it tells you the focus is 12, 0. It tells you the directrix is equation x equals minus 12. You know, for most parabola centered at the origin, there's not much left to do now, is there? So we've got the equation of the directrix. Here it is here. Now we want to show that the equation of the tangent to C at P is okay. In general, what is the equation of a tangent to a parabola? Well, we take the equation and differentiate it implicitly in both sides. 2y, I guess I'm going to go y dash equals 4a. All right, so I guess well, what does that even mean? I guess I'm differentiating both sides with respect to x, right? So the dy by dx is here, and the other side becomes 2a over y. That's the gradient at any point, so it's dictated by y. So in our parabola, a was 12, and we're asked to find the gradient at a specific point where a is 24t. Sorry, y is 24t. So what we're gonna go there is 24 over 24t. So the gradient is 1 over t. That's kind of nice. If you see an answer like that, you probably know you're on track. Okay. So then we're like, okay, well, if that's my gradient and I have P as a point, well, it depends what you do. I have this equation. So y minus y1 equals mx minus x1. Seen that equation before? You can get straight line equations pretty easily from that. y1 and x1 are your points. So in this case, it is going to be, what was it? Was that 24t for y? Yep, 24t for y and 12t squared for x. Okay. Now, well, just simplify. Okay, so multiply it by t here. Remove the brackets. And we see that this guy becomes minus 12t squared. And it would make sense to make, well, is that just it? Yep. We're just going to write, yeah, we're going to move the other stuff all to the other side. So this guy will go over here and y will go over here. So we see that we're going to have x minus yt plus 12t squared equals 0. Perfect. Now, the tangent to C at the point 312 meets the directrix of C at the point x. Remember, C is our parabola. So we're introducing a few more things now. So this is an equation for a tangent at general point. So 312. So it's on C, 312. We don't really need to double check. We just know that y is 12. Whoops. Just change my brush size radically. Okay, we're given there that y is 12 and x is 3, I think. And we can calculate our t. And Hope that's 0. So we're asked to find the coordinates of x. So it meets the directrix at the point x. So how could we do that? Well, what I'm going to do is, we have our directrix, remember, our directrix is x is minus 12. So these are the coordinates, not of the tangent, but they were the coordinates where the tangent meets the curve. And they actually give us a t. They don't give us our x and y to plug in here. They give us a t. Now we can get t in two ways. We can just plug them into the equation and find out what t is explicitly, or I could just compare them each to the points. So free is 12t squared. Okay. Is that, yeah, so free equals 12t squared. And then we have, what was it, 24t equals 12. I mean, both of those give you t as a half. This one actually gives you two answers, but you know, this one again reminds you, hey, there's only one answer actually. And it's t as a half. So we have t equals a half, so that'll give us our straight line required. And then we're plugging in a value of x into here. So let's do that both at once. Yeah. So hopefully I'm correct in saying that y is 18. Does that seem to make sense? Well, plug y into the equation. You get a 9. X is minus 12. Plus 3, yep. I guess it meets it at y coordinate 18. Of course, the coordinate of x is going to be minus 12, just like it was on the directrix. Okay, so moving on to the last question, which is a bit induction, okay? So induction, you just need to prove this for n equals. So n belongs to positive integers, so we will start at n equals 1. 3, 0, 6, 1 is the left-hand side. What's the right-hand side? The right-hand side is going to be, when n equals 1, 3, 0. That's 3 times 2 and 1. And you see that the left-hand side is the right-hand side there. Because 3 times 2 is 6. All right. So that's fine. Now what we need to do now is so forth. Prove the inductive step. So we assume it works for k and we try and prove it for k plus 1. So assume that you can write 3061 to the power of k. We assume that can be written as 3 to the k 0. 3 is 3 to the k inside the brackets? Yes, it is. Times 3 to the k minus 1. Oops. There you go. And 0. Okay, and you know what we're doing here is we're saying that we assume that n equals k works. So assume this case is true. And we want to somehow from this get to the next step. And I guess the most natural, intuitive way to do things here is to multiply on the right by another dude here. Okay. It's 3 to the k, 0. Let me write that a bit neater again. 3 to the k minus 1, 0. Multiplied by 3, 0, 6, 1. Okay. And what does this lead to? Of course, this leads to 3, 0, 6, 1 to the k plus 1. And we see this is equal to what? Well, if we use matrix multiplication to expand it out, let's just draw rings around it so we don't get confused, yeah? So we get 3 to the k plus 1 straight off. I guess because it's induction, you should probably denote what you're doing rather than just skipping algebra and writing down the answer. But I mean, it's too easy. We see that the zeros are canceling and stuff. But what you would do in the exam, I guess, is be really rigorous about it. Kind of like this. F3 to the k times 0 plus 0 times 1. Then we have, I guess, what is this? This is 3 squared, 3 to the k minus 1. Yeah. Plus 0 times 6. Is that a 0? Nope, it's a 1. My bad. Yeah, I thought so. Plus 1 times 6. And we're going to get, the last bit's going to be 0 plus 1 times 1. We can clearly see this matrix is going to be, you know, the case that we want there, right? Yeah. Because it's going to be 3 upon, if you think about that, that's going to be 3 to the k plus 1. I took one of the k's inside. I would like this to be a minus 3. And it will be, because currently it was a minus 9, right? The 3 squared is minus 1 is minus 9. But then I added a 6, and it got back to what I wanted. Okay, so that's good. And then, of course, this is 1. So we just write a little inductive step. N equals k implies n equals k plus 1. Therefore, you know, something along these lines, you know, 1 implies 2, implies 3, implies ... Therefore, true for all n positive integers. Drop my pen, whoops. Okay, so then we get this divisibility question, which is, I'll drop my pen again. This is quite an interesting question. Okay, I mean, first of all, again, n is a positive integer, so you prove it for n equals 1. And it's pretty trivial. In that case, you're going to get 7 plus 5, which is, of course, divisible by 12. Now, how are we going to do this? Okay, I'll show you the way I like to do it. So what do we have? We have f of n is 7 to the 2n minus 1 plus 5. Now, I assume f of k is 7 2 to the k minus 1 plus 5. Now, if we can show that f of k plus 1 plus some multiple lambda of f of k is divisible by 12, if we can show that this is divisible by 12, what does this mean? Right, so assume is divisible by 12. It's a pain in the ass to write divisible by 12, so what I can write is 12 divides this thing, and we want to prove that 12 divides this thing. Okay. Now you may wonder, what? Like, what is this? Where have you come up with this, Chris? I don't understand. Well, that's what I thought when my teacher showed it to me as well. But after a little investigation, little empirical investigation, I was like, okay, I accept what you're saying to me. Because basically, if this guy's divisible by 12, and lambda is an integer, so lambda is an integer, then, well, if this whole thing's divisible by 12, it directly implies that f of k plus 1 is divisible by 12. Okay? Think about that for a second. If this whole expression is divisible by 12, well, it must mean that this is divisible by 12. Just think about that. It makes sense, right? If you want me to write a bit in the comments, I will explain it. But yeah, it took me maybe a few days or something to you know, thinking about it before I clicked on my brain. Like, I see. It definitely is. You know, there's no other possibilities. So if we can prove this divisible by 12, we basically proved the inductive step. We said that f of k implies f of k plus 1. And the reason why this is cool is because, well, let's write that. What is this thing? This is going to be 7, 2k plus 1, plus 5, plus lambda 7 to the 2k minus 1 plus 5. Can I write that as anything simpler? I can. See, this lambda trick's actually very helpful. Okay. That's how much 7 to the n minus 2n minus 1 I'm going to have. Was that it? Yeah, it was that. Okay. So that's the case. That's what we have there. And that's that thing there, okay? Now, how could this be divisible by 12 for some? If it's divisible by 12 for any value of lambda, f of k plus 1 is also divisible by 12. So, perhaps we should choose lambda equals 11, because then this guy would be 12. That would be 12 times 5. What would this guy be? Oh, that's nice. It would be 60. 60 is divisible by 12. Okay, so when lambda is 11, this whole thing's divisible by 12. Okay. And therefore, that implies that f of k plus 1 is divisible by 12. Right? Therefore, 12 divides. Yeah. So I guess. So we've showed that f of k true implies f of k plus 1 true. And again, induction, I'm open to any suggestions on how to improve these videos, by the way. I'm just kind of starting out. Any feedback is greatly welcomed and encouraged. If you want me to do more of any types of questions, just leave a comment below and I'll get to it as soon as I can. So that was FP1, and it was pretty nice. This is Chris, and I'll see you in the next video, provided you're still watching this and are enjoying the content.